Thank you, everyone. I'm David. I'm a PhD student here. It feels scarily recently that I was on the other side of this in the audience to choose my university course. So seems very strange to be here. But what we'll do is we'll have a look at aiming for all-purpose robotics and how do we design robots as adaptable as us. But before we kick into that, let me just explain why I'm here, how I've got here. So here I am, that green dot there is me at the moment. It's been probably about a year since I've used these slides, so I've just got to move that green dot along quite satisfyingly. But yeah, so I arrived in Cambridge in 2016 for a bachelor's in engineering at the time. So here I am in that year in 2016, that's me finding out about Cambridge punting for the first ever time and clearly posing for this photo. But yeah, so I came in to do engineering at Corpus Christi, which, as you may well know, or if not, you will almost certainly be told again today, starts off as a 2-year general engineering. So you don't specialize within your first 2 years. You cover pretty much every aspect of engineering. So mechanical, structural, civil, electrical, and a whole host of others. And then you don't start specializing until your 3rd year of the course. So in my case, that was for mechanics and materials. Probably what I would have chosen to specialize in when I was originally applying, but I definitely don't regret having those 2 years. It's really useful to get a much bigger overview of what's going on and to know how other things work as well. Definitely don't regret that. So then in 2019, I finished that. I started the Masters and continuing a trend of embarrassing photos from that year. There I am at the Freshers' Fair of that year as well. And this was pretty similar. The jump from bachelor's to master's in engineering is not much of a jump, really. You're still at the same college, so still at Corpus, still doing the same subject, engineering, and still specializing in mechanics and materials. The only big difference being that you now have a single thesis project that you spend half of your year working on. So for me, the question behind that was, can we 3D print vinyl records? Which meant I could spend a year looking at the precision of 3D prints and looking at the microscopic effects in this groove of a record. So if you have a look at the dates of that year, you might not be too surprised that the second half of that ended up being quite a lot more in simulation than we expected it to be. But we had a look at the dynamic effects on the turntable then and simulating these errors and how turntables work, which was still nice and interesting and still meant we could write the thesis. And yeah, the answer really to can we 3D print vinyl records is a big conclusive kind of. Yeah, you can get the resolution there to get some kind of music out, but it's not enormously good quality at the moment, which I think we knew before we started really, but was still good fun to try out for a year. And then if we move along, here I am now. That's me in my PhD years. And there's a bit more of a jump at this stage from the master's to PhD in that I'm now working in a specific lab rather than being taught by lectures all the time. That's the bio-inspired robotics lab in the engineering department, led by a professor from Corpus, actually. So we all knew him already. And I had a taste of this between my bachelor's and my master's in 2019. I stayed here one summer and worked in this lab. And at that point, I had a look at how robots can continue to learn to walk when you're changing the dimensions and the shape and the weights of their bodies. So you can see in these 4 videos, hopefully you can see that all of these robots have slightly different sized feet, but they're all still learning to continue to walk without falling over when you suddenly put a much longer foot or a much shorter foot on it. And so I was looking at how we can adapt to that most efficiently. And then since then, I've been working my PhD on various different projects in this lab. Lots of focus on soft and flexible sensors, but lots of other projects as well. So here is very much a visual overload of various things I've done in the last year and a half of this 3.5-year course. some of which I'll touch on as we go through these slides, some of which I've solely put in here because they look quite cool for the slide. But yes, those that are relevant, we will talk about in the next few minutes. Obviously, it's not just me that works in this lab. There's a whole host of us doing a big range of projects. So I've got a bit of a compilation, which again, hopefully videos come across. So various people work on different hands to pick up a variety of objects and do other tasks. Here's a soft and flexible finger, which has sensors to sense what it's touching and how hard it's touching it. This is looking at how seeds from trees flutter to the ground, depending on the shape of the seeds and how we can control and or predict how that falling occurs. And then the same thing for dispersal on water with waves coming out from a pond, for example. And some people even have a go at harvesting some lettuce with robots, which is a surprisingly difficult problem, actually, not just in the mechanical aspect of having to slice lettuce from the ground, but also there's a camera on here that's identifying the field of lettuce, picking out each individual lettuce, deciding which ones are ready to be harvested, and then moving that robot to the right position. So that's surprisingly impressive project there. And then there are many others that I haven't included here. There's about 15 of us in the lab, I think, so various projects going on. Some notable emissions includes various robots to help in healthcare, so to help doctors do some remote examinations. So if they're not near the patient, they can still make some diagnoses if you have a robot to connect the two and perhaps perform some examinations. And we've even got a robot chef in a kitchen downstairs that's been cooking some scrambled eggs and omelets for us. So yeah, a whole range of projects. So with that in mind, knowing that I can't cover everything in this talk, what we'll sort of sprint through is what the state of robotics is currently like in the world, what you see, what still needs improving to get us to the futuristic visions we probably have of robots, how we can actually get to that stage, and then along the way I'll scatter in some examples as well, wherever that would be useful. So yeah, starting at the top, the first question is, where are we now with robotics? If you Google robots as of yesterday morning, this is what the Google page comes up, what you see. So lots of humanoid metal boxes, really ties in with maybe Terminator visions. We have similar things. Some of these are physical products and robots that have been made in research. Some of these are computer graphics. But what we're seeing is often the vision that we have is that robots are fairly similar to us and will do similar things. Whereas the robots that mainly exist, probably most commonly and most widely used, industrial robots. So putting together cars, these huge arms, or moving things around a factory floor. You see them in use because they can do exactly the same thing very precisely and very repeatedly again and again and again. And that's very useful for manufacturing, obviously. You don't really want to be near these robots when they're in operation, so they're pretty dangerous. You keep out their way. They do the same thing. Whereas we see other things, maybe in restaurants, robot waiters, which are designed to be slightly more collaborative with humans while still serving one specific task, which is to take your order, deliver you some food. So much so that you could probably foresee nearly all of the situations this robot would ever find itself in. So you might even be able to code in every situation for this specific task. Whereas a big goal of robotics is not having to do this and being able to adapt to any situation that you see. That's not as much coded into anything at the moment. I think one of the closest we have was these toys you may or may not recognize. I don't think the company exists anymore, but these were Anki vectors, though they didn't really serve much function other than looking quite sweet. They could learn as they went and learn new aspects of their environment. Robots that learn but do have a function, we have Roombas or robot hoovers of various brands. They can learn their environment around them, but they are solely there to clean your floors. They're not going to learn to do anything else new. Some companies work on more adaptable robots. So again, you may have seen Boston Dynamics have a big range of robots. This is probably the most famous one, Spot, which is much more suited to a range of applications, and you can teach to do different things. And then finally on this slide, we'll go to a much higher level in the intelligence of the robot rather than the body of the robot. There's a lot of artificial intelligence research going on in the moment. What a lot of people see as a major breakthrough moment was when artificial intelligence made by DeepMind beat the world's best Go player at what's considered a very, very hard game. So a human being beaten for the first time at this was seen as a big breakthrough in artificial intelligence, so in the brains that we're putting in our robots. Big difference between what I'm saying here and what we picture robots maybe being in the future is this idea of whether they're single objective, whether they're made to do a specific task, or whether they're multi-objective and could potentially do anything. So we're very good at making single objective robots. We can make lawn mowing robots. We make robots that can operate on patients. If you consider a smart dishwasher to be a robot, then we can make robots that clean dishes as well. But what we might picture in the future is something more often humanoid, but something that can do the range of tasks that we can. And that's not quite what we see just yet. I'll come back to this picture in the middle, this Baymax, a bit later. But yes. So largely a reason for that is something called Moravec's paradox, which, as described by author Steven Pinker, said the main lesson of 35 years of AI research is that the hard problems are easy and the easy problems are hard. The mental abilities of a 4-year-old that we take for granted, recognizing a face, lifting a pencil, walking across a room, answering a question, in fact solve some of the hardest engineering problems ever conceived. So yeah, what he's saying there is that things we might consider hard, like beating the best ever Go player at Go, are comparatively easy to things that we think are easy, like making a cup of tea and the processing involved in that, for example. And to prove to you that is a thing, absolutely incredible compilation video from a very high-end robotics competition in 2015 here, where we can see all of the robots falling over because of the unexpected environments they found themselves in. We are very good at making robots that can know what environment they're going to be in and cope with that. But if you put them somewhere unexpected, there's so much noise that you're going to get a lot of failures. I'm admittedly biasing this a bit by showing you only the failures, but they're the more interesting bit. We see a whole host of types here. So we see sort of purely mechanical failures. We see computational failures where noise has just given us some kind of error. We see almost dead reckoning failures, which is where we're offset from the position we think we are, like here. We think we've grasped that, and we're a good meter away from where we thought we were. This is purely mechanical, and yeah, we will watch this to the end. I think we're nearly there, and it's just entertaining to see. All right, there we go. I think that's it. So why did we see that? Why is designing robots for this unexpected environments just so difficult, or to be adaptable to whatever we want them to be? And the major reason is that there's a huge range of tasks that we could be asking an all-purpose robot to carry out. They might be physically difficult, they might be mentally or computationally difficult. And yeah, our bodies are designed to do a really surprisingly huge range of tasks. I can use my hands to thread a needle, but I can also use them to carry a piano down some stairs. And it's difficult to make something that has both of these ranges built into it. Or yeah, mentally, computationally difficult, something like playing chess or playing Go. But even just the fact that we can stand up and stay balanced is incredibly computationally difficult. It's not something we consciously think about most of the time, but to get a robot that stands up and doesn't fall over, you have to constantly take these signals that would effectively be from our muscles of whether we're starting to tip or strain in a direction. That's fed back to the brain. That processes whether we're about to fall over, how to compensate for it, feeds that back, and we automatically correct for it. And obviously that gets much worse as soon as we start to walk or we start to run. That becomes even more difficult as it becomes more and more of a dynamic problem. And as the name suggests, that's what the company Boston Dynamics are very good at coping with, are those kind of difficulties. But then there are various other difficulties as well. So if we have an all-purpose robot, how do we prioritize which task it should be trying to complete at a particular moment? So, for example, if I had a helping robot here in my flat and I told it to go and wash the dishes, it first needs to process all of that information, process which dishes I most likely mean, what I mean by washing them. And then it needs to start to plan that activity. So it needs to know it needs to make its way to the kitchen, it needs to make its way to the sink, find the dishes, find a washing up brush, for example, before it can even start that process. But it needs the ability to change that on the fly. So if it starts making its way to the kitchen and encounters my dog, its immediate priority needs to be don't step on the dog. It needs to have this avoidance built in so that we can avoid that. Or similarly, if it starts washing up the dishes and then senses that the entire house is on fire, the dishes are probably slightly less of a priority by that point, and we might want to switch to helping people escape the house. And that's difficult to do. There's almost an infinite range of possibilities that could occur. And in most cases, we can't realistically code every single case into our robot. So we need to start being clever with how we learn about them. Fairly similar is that a lot of what we do uses knowledge that we've only built from experience. So if I'm washing the dishes, I know the texture of the plate. I know how heavy it's going to be when I pick it up. I know how much force I need to apply to get something relatively clean, or if there's a hard stain, how hard I need to scrub it. I know that once it's clean, I shouldn't frisbee it back into a cupboard because it'll shatter the plate. But I only really know this because I've done similar things before. I've handled plates before. That's not necessarily something I could get just by looking at the particular task. Or I don't know, if I looked out of my window behind me, I can see my bike outside. I know that I can't reach it because there's a window in the way, but there's not necessarily, as long as my window is clean, anything to tell me that. It does look like I should just be able to reach it. But somehow my robot needs to know there is a window in the way there. So what comes out of this, and is similar to the problem before, is we can never really write down every single situation. We can't write down all of physics in a way that we're going to interpret. So we need to somehow constantly learn about our environment, learn new things, and adapt our behaviors because of that, which is a very difficult problem, especially when we're in totally unknown and new environments. So how can we possibly deal with these huge range of problems? To simplify it hugely, we've got two options. We can look at the brain of the robot. So we start changing maybe the architecture of the brain or the decisions that it's going to make. So very simple example we've seen already was looking at how we cope with walking when the foot size is changing. That's all something that's done in the brain of the robot. It's not changing its body to cope with that. In fact, it's coping with the change in its body. But the alternative is change the physical design of the robot. It doesn't necessarily have to look like we picture robots, which is these big rigid bodies that move very unnaturally. The reason we have a dance called the robot is because it's so unnatural. But that doesn't have to be the case. We can focus on designing the body to avoid or minimize some of these problems instead. And so what we'll do in the time we've got left is just have a look at a few possible approaches that we can design the body of our robot to minimize these. So one example is passive dynamics, one is emergent behaviors, one is evolution, and then we'll end with something called soft robotics. So we'll go through these one by one. All of them, to an extent, are subfields or examples of bio-inspiration. So being inspired by biology, which has had evolution to have billions of years head start on us. So using that can be very useful in a lot of situations. That can be as simple as modeling animals as mechanical systems and transferring that across to our robots. It can be more anthropomorphic, so physically trying to make human hands, for example, or even on the material level, trying to make materials which are more like our skins. That can be very useful for a whole host of reasons. Our skins are very adaptable to many tasks. Or it can be pretty much pure biomimicry, where we copy something that nature's made well. An example that comes up a fair bit in robotics is copying octopuses or octopi directly and using some of the interesting features of them. So what we'll do with those four, I'll put them up here and we'll go through them very quickly, really, one by one. So we'll start off over here. What I'll say is some of these are, in the time I'm giving them, a bit tricky to wrap your head around. So if one of them's not being particularly clear, no need to worry. We'll soon move on to the next one, and I won't use any of the things I've said in the prior one for that. So just in case I'm going through things too quickly, we'll soon be away. So passive dynamics is our first example of how we want to design our robots. And it's looking at how the robot's body behaves totally passively. So when you're not giving it any kind of movement instructions, you're not actuating it at all, just how it behaves and interacts with the environment in that case. So an example I showed you a bit already is this passive hand here. So we're moving it up and down from the wrist effectively, but this hand itself, we're never telling the fingers to move or open or close. They're just attached to springs. It's anthropomorphic, so designed on a human hand, sprung at a certain weight. And just with that, this hand can pick up a big variety of objects. This is work done by Kieran, who's a PhD student in the lab as well. He's just coming to the end of his PhD. And he's got a whole range of examples of how these anthropomorphic hands can really help the passive dynamics and help us make really efficient robots. So yeah, if you consider designing a hand like this and then combining it with adding motors and being able to make the fingers move, it significantly reduces the control that we need to use. If our hand by itself is able to pick items up already, we don't need to add much to that to be able to then pick up whatever we want. So I'll stop that there because that does keep going. Yeah, there are two main examples that come up, I think, when you talk about passive dynamics in robotics. They're older examples, so neither from our lab, but both I think very interesting. The first of which is a passive dynamic walker. So can we use this principle to design robots that walk without any sort of actions being given to them? So without us telling them or giving them motor signals to walk. And here's an example of a robot doing exactly that on a treadmill. The treadmill's pointed slightly downhill, so the only energy that's being applied to this robot is just that of gravity, and that's enough to get this thing walking fairly similarly to how you'd see a human walk, though with a different number of legs. But yeah, if you just put this at the top of the hill, it would walk down like this. And you can imagine, again, if we designed a robot like this, it hugely helps it to be much more energy efficient. If we're able to walk without any motor signals, then as soon as we start going uphill, we can apply minimal motor signals to do something similar. Then the second example is that of a swimming fish. So this is an example from MIT in 2006. Took this video of a fish from above swimming upstream. So there's a constant stream of water firing down, and you can see the fish swims up it, hits the top, comes back. But the remarkable thing about this video is that the fish in this video is dead. So this fish is totally passive. It's not making itself move at all. And the swimming that we see here, in fact, I'll just play that again, is purely just because of the shape and the design of its body, really. When it encounters this stream of water, that's enough to get it to start swimming, and that's enough to get it to start moving upstream. So when this fish is alive, it's actually fairly computationally simple to get it to swim up this stream. And again, much more energy efficient if we can incorporate those sort of principles into our robots, where they can then always swim or always walk without us having to put much effort in on the control side of things. Okay, so that's number one. That's a brief look at passive dynamics. There's a lot more to it if we had time, but we'll move on to something else, which is using emergent behaviors. I think this is the hardest one to get your head around, but emergent behaviors, very simply, are behaviors, complicated behaviors that stem from a very simple set of rules, just repeated lots and lots of times. So the classical example you may or may not have seen before is Conway's game of life, which is just a black and white grid. At any moment, a square in that grid can be colored black or it can be colored white. And at the next moment in time, we choose whether it's colored black or white, depending on what color its neighbors are. And we can define this in a really simple set of rules. But just from this really simple set of rules, this game produces really complicated and intricate patterns, which we can start to almost infer behaviors off. So it looks like something's being fired out down to the bottom right here. We've got things oscillating back and forth at the top. And that's all come out of this really simple set of rules. And in fact, this game has been shown to be Turing complete, which means that technically this could do anything that a computer could do as long as your grid size is large enough. And that's all emerging from these really simple rules that we've defined. But yeah, maybe that's not so clear why that's useful for robotics yet. So another physical example that comes up quite often is how the really intricate pattern of a snowflake, notoriously complex and beautiful, emerges from really low level interactions between particles, the attraction and repulsion, are fairly simple behaviors that just, as you scale up, produce this very complicated pattern. Again, might not be obviously applicable to robotics. So another example is the swarming of birds. So we have a look at this really beautiful behavior. It's like birds, the same with schools of fishes, produce patterns like these. But none of the birds in this swarm is picturing this pattern and how it can make it in its mind. Let's play that again. Every single one of these birds is just following some fairly simple rules based on how close its neighbors are and the direction it vaguely wants to head. And as you scale that up to a bigger system, you produce these much more complicated patterns. And in fact, that was shown quite famously by Craig Reynolds in a simulation. Examine these rules by giving each one of these arrows, these voids, different rules to follow. And when you scale that up, you can start to see these similar flocking behaviors come out. So hopefully it's maybe slightly easier to see now why we might want that in robots. So we could apply that most straightforwardly, I guess, to drones or to swarms of drones. We could apply very similar flocking behaviors without really complicated control mechanisms being needed. So the field of swarm robotics in general is very useful for that, but emergent behaviors, without going into too much detail, can be used to solve mazes as well, using biological emergent behaviors. And then directly in robots as well, incorporating reflexes is quite a nice example of using emergent behaviors. So apologies for this stock image, but if you incorporate reflexes, so if you know that something bright flashes across my field of vision, I'll reach out, and if my hand hits an object, I'll close my fingers, then we might start to get emergent behaviors where I suddenly pick up a water bottle just by moving nearby. or slightly more complex behaviors allow us to get much more complicated things happening with fairly minimal control effort. So yeah, as I say, I think that's the hardest one to wrap your head around. So if that's not too clear, don't worry, we're going to move on now to the idea of evolving robots. So much like biological evolution, which has produced a big range of very capable organisms, we can try and use that same process to evolve robots over a shorter time period and get a whole range of behaviors out or evolve towards some particular function that we want them to complete. So what I've put here is the process of evolution, but worded very, very strangely. So bear with me on this, in that I'm saying our DNA encodes the details of us. It's a method of encoding all of our information as DNA is how we start off. That's then produced into a human. So through pregnancy and birth, that DNA is turned into a physical organism. We then live our life. I'll come back to this in a second. And if we reproduce in our life, our genes may or may not be mutated, but they're combined with someone else's genes, and that's encoded into the next generation who are produced and then live their life and then reproduce. And we just keep going around this cycle for each generation. So the reason I put in evaluate here is more similar to robotics, but I'm saying that life is then survival of the fittest. So it's almost an evaluation of how successful you are, whether you find a mate and are able to reproduce. Again, very strange way of phrasing it, but that makes more sense when we think about it in robotics. So in a robotic sense, our encoding shouldn't be DNA. It should be some physical code on a computer normally, which describes a robot that we want to make. We normally put constraints in, so it can't be anything. It might be, I want a robot that looks like a human. It will have a foot length of 5 centimeters. It will have a leg length of 15 centimeters. It'll have a hand size of, I don't know, 5 centimeters again. And just these single rules encode the properties that we want. And then from these properties, we can make our robot physically in the world. We can produce it. Things like 3D printing technologies are really, really useful for something like this, because we can turn this computer code into a physical robot nice and quickly, which we can then evaluate for a particular task. That makes more sense now. Often we point a camera at it, use motion capture software, which you probably know is something like this with shiny balls on a suit in front of a green screen. But you can point a camera at a robot, use exactly the same technology. You can track how it moves about and evaluate it against how well it does something specific. So we might want to make a robot that, for example, can jump as high as possible. And so we will track its motion. We'll see how high it can jump. We'll evaluate that. If it's fairly good, its genes might live on to the next generation, where they may be mutated, but they'll be combined with some other information and we'll produce our next generation of robots. And hopefully then over a few different attempts, we start to find robots that can jump higher and higher and higher, and we evolve them over this space. So this is early days for this research, really, which is why I don't have concrete examples, but here's a fairly straightforward one from a few years ago in our lab, where the robots were very, very straightforward. They were just some cubes stuck together. So our encoding was very easy to define. We could say, this robot here is just 2 big cubes stuck together at this position with a small cube stuck on the side in this position. And that's the encoding of our robot. That can be produced by a bigger robot, evaluated by its ability to move, and then new generations are made. So I've got a video to show you what I mean here. The encodings happened off screen in a computer here, but we're now in the producing stage. So this very simple cube robot is being produced bit by this bigger robot arm. It's got effectively a hot glue gun incorporated into it. That's how it's sticking everything together. It needs to get it all at the right orientation, which is why it's spinning everything about so much before beginning. But we apply some glue now, we stick it together. So we've now produced this generation that can be evaluated. So there's a camera pointed at it now. If that had been successful, so if we'd wanted something to move in a circle, then that might be good. We might then produce a next generation that's fairly similar to this. If, for example, we'd wanted that robot to move in a straight line, that might not have been as successful. So we might not take as much notice of the encoding of that robot when we try and make future generations. Okay, and then finally in our list is this idea of soft robotics. An enormous field by itself. I definitely don't have time to do it justice. It's easily a whole lecture or a whole university course or whole lecture course by itself. So it's going to be a very brief overview of soft robotics. But you can almost guess what it is from the name. This is how we view robots in Google. If you change that search to soft robotics, you get a very different world of, well, soft and flexible things, often inflatable now. And they start to look a lot more biological. They're much more similar to organisms in the world rather than rigid robots. Yeah. For a full overview of this, I really suggest you watch this video by Veritasium on YouTube called Why Robots That Bend Are Better. I've put in the very intro of this video here, just so you can see a couple of them moving about and how different they are to normal robots. The sound wasn't playing ball, so I've just put subtitles on, which I'll read out to you. So these are soft robots. Their structural components are built not out of metal or wood, but flexible materials like plastic tubing. But how do they work? And why would you want a soft robot in the first place? And then that's the end of the introduction. So I hope that gives you some motivation to go and watch the rest of that video. As I say, it's a really nice overview of the field. And you can hopefully see from some of those examples that soft robots are very, very different looking. Here are some examples that we work on or collaborate with in the lab. So here's a soft ring which can grab things inside it and move them about. Here are some soft fingers picking up difficult to pick up objects like a coin. This is a bendy inflatable finger made out of jelly that can sense what it's doing as well. And this is a hand made out of self-healing materials, which once they're damaged can heal themselves like our skin over time. But yeah, just to finish off, some advantages of soft robotics include that they're much safer to collaborate with. So if something were to go wrong, you'd much rather a big lump of inflatable silicon headed towards your head than a 3-ton chunk of metal. So in lots of applications where we work with them, soft robots are much more preferable. Similarly, for delicate interactions like agricultural automation, picking fruit is often an example of where we might want something soft and delicate, so we don't just crush an orange as we pick it off a tree. And they can adapt to their environment. The fact that these soft materials can change shape and can change size. Similarly, they can squeeze through small gaps. That seems quite minor, but if we want to, say, deploy a robot for some kind of rescue purpose, someone's stuck in a cave and we're trying to deliver resources to them, a robot that can change size and shrink down is going to be much more beneficial than something rigid and solid there. And then finally, in some ways, these are much harder to damage, so you can't crush them, you can't, I guess, snap them as easily because they're so soft. But then first up on my disadvantages list, in some ways they are easier to damage. So you can't really pop or puncture a normal robot, but you can pop or puncture an inflatable soft robot, which is why materials like this self-healing material down on the bottom left is very useful to incorporate in because we can recover from these damages. Another thing that's worth mentioning when you see really fancy videos of soft robots is there's often a big noisy air supply just off screen of the video you're seeing. Because they're inflatable, we need a source of compressed air. which is very often a downside to the system. And yeah, for the full benefit to the previous slide, sort of rely on everything in the robot being soft. So that includes our air supply, that includes our brain, that includes our sensors as well, and our batteries. And yeah, there's a lot of work going into making all of these components soft, but it's a long way to get everything flexible. A lot of my work is on flexible sensors, so in this specific niche of soft robotics. And then as well, they're much harder to control. So normal robots, we know with the joints in this position, everything's going to be in this position, but a soft robot can technically deform to any position. You can bend it, you can flex it, you can twist it. So it's much harder for a controller to know where it's going, where it is. But that just means we have to apply often some kind of neural network or artificial intelligence in order to deal with this more difficult control problem. So that's some downsides of soft robotics, but on the whole, this is a big field going towards how to make these robots much more adaptable. In this sense, there's a lot of promises for it to solve some of the problems we talked about earlier. Hopefully that makes sense why I had this inflatable robot on screen earlier, just to tie in to make everything much more adaptable. And yeah, I'm dead on 11:15, so I'll leave things there. If we've got time for any questions, I'm more than happy to answer them. I'll look through the chat if not, or finally, that's my email down on the bottom right there. More than happy to hear from you. So yeah, thank you very much.
Thanks, David. It's always a good sign when a historian can follow the talk and get what you're talking about. So I appreciate that from just for myself. A couple of questions to start us off. So this is, let me go to, So you briefly touched upon this in your talk, but surely making robots humanoid decreases their effectiveness. They aren't adapted to this kind of body. Wouldn't there be an easier body for them to control?
Quite possibly, yes, but no one really knows. So for specific applications, if we want a robot that does something very specific, then yes, almost certainly a human's not going to be the case. We know that we're very multi-purpose. We can follow a whole range of tasks. So when we're trying to produce something called purpose, that seems like a good starting point. But the benefit of something like evolution in robotics is we can see what we can make and try and come up with something totally different and useful. But yeah, very good question.
Hannah asks, what type of programming is used when coding robots? Procedural, object-orientated, etc.?
Things I'm doing, which are admittedly very much at the prototype stage, tends to be generally object-oriented stuff I'm doing. Yeah, that's written often in MATLAB or Python, but late robots in use are generally more embedded, something like C. There's research into different architectures you can use. So totally different things, something called subsumption architecture was quite popular for robots for a while. I don't think I know much more about that, to be honest, to be able to explain it. But yeah, that's the field at the moment.
Okay. Laura asks, what made you choose this specialism?
It sounded interesting when I originally wanted to do a PhD and did this internship in the lab between my bachelor's and my master's. So I hadn't done much robotics before that point. Then I worked in this lab for 10 weeks and then was very, very happy to come back for a PhD after that. But yeah, it was actually just getting some experience for 10 weeks.
So someone just wants to, so you talked about the emergent behavior. You might have talked about this, I might have missed it. Is there any examples of emergent behavior that is currently being used in robotics?
Yes, largely actually on the software side. So I mentioned, or briefly mentioned, reflexes lead to often emergent behaviors. So simple rules. If this happens, then do this. You can build that in mechanically. So if your hand hits an object, it should just grasp around it automatically. That can be done mechanically with sort of motions in the hand. in the actual brain, so in the control side, they're used a lot, often to solve problems, because you can run something lots of times and use these results of these simple rules to have a look at what they're doing. So things like maze solving, I briefly mentioned. There's an emergent behavior where you can solve a maze based on how ants interact in the world. And that's encoded into various maze solving algorithms. But yeah, there's probably some other examples, but not that are coming into my head at the moment.
Hassan asks, has it ever been considered to combine soft and hard components similar to how humans have flesh and bones?
Yeah, exactly. And that's, we've got a PhD student who does very much that, like flesh and bones, so in hand. So that is a really good way forwards. It's hybrid robotics, I guess, then at that stage. Often when we try and make soft robots, they end up being a combination anyway, because not all of our combinations are soft just yet. We often have to include hard components just because they all we have. So we might have a soft finger connected to something rigid to hold it in place and control it. But yeah, again, replicating what we have in nature, which is flesh and bones, as you say, looks like a good path to be taking.
George asks, how do you ensure fault tolerance within robotic systems?
So there's lots of research in deployable systems, how you'll cope with things like this, and some things you want to never fail. You want lots and lots of systems on. Admittedly, what I'm doing directly in research, there's very little of that. So we look at sort of prototyping stages where if something fails, it's not as concerning. But as you go up and up to something you're going to deploy in the real world, you want a lot more of that. Everyone's concerned about artificial intelligence and the singularity. So there's a lot of ethics behind how we should constrain our artificial intelligences so that they don't turn against humanity. And the ethics behind that is a big field in itself.
Is there any way biological aspects could be used alongside robotics, for example, stem cells, to create a more adaptive machine?
Really nice question. I've seen some people do some similar things, so I can't remember many details to have a clear answer, but I've seen this combined with this evolution cycle in robotics, where they're designing in a computer and in simulation different shapes of small robot, and then making them by combining cells together and physically testing them in the real world. I think they're frog cells they use for that. Yeah, it's cool to me, but I often don't know what's going on when I see that happening.
Okay, so I'm conscious that our undergraduates are waiting, so I'll ask one more question. So the 4 types of technologies you were talking about at the end, are they always applied together, or do you apply them separately?
Can be any, really. So often just one aspect is useful for making some things. In an ideal all-purpose robot, we might apply or try to apply all of them, plus many more principles that I didn't have time to cover. But yeah, in an ideal world, we try and get some aspects of all.
Okay, and I'll ask what, because you answered that quickly, I'll ask one more.
Yeah, of course.
With the evolutional progression that you mentioned, how much can this process be done autonomously, or does it still require a lot of human input into the evaluation?
Oh, again, really nice question. Autonomously is the ideal. That's what we aim for a lot. So if you can get something that 3D prints and then tests itself automatically and then can just start again, you can do this evolution without being there. And that's what we try and set up a fair bit. There's also an alternative that I didn't really mention, that a lot of that testing can be done in simulation. So you can design a robot, simulate how it might behave, which means you don't need to make it at all, and then evolve it just in a computer. The downside to that is there's often a big gap between how something behaves in simulation and how it behaves when you actually make it. So we often have to combine simulation with this real world testing to get something a bit more realistic by the end.
Okay. Well, we've taken up a lot of your time there, and the undergraduates are waiting. So I'll say, on behalf of everyone, David, thank you very, very much.